Now that gain is nothing but what? We can say that that is about a whichever the practical antenna we are using, and that practical antenna radiation intensity in a theta direction divided by that isotropic antenna, isotropic antenna in the given direction. So we need to find out what will be the power radiated in the given theta direction, and then what will be the power radiation in the same direction with a isotropic radiator. Now isotropic radiator means what? It radiates the signal in all the directions. But in the case of a antenna, we need to consider that a isotropic radiator that radiates the signal equally in all the directions. So that's why we can use that isotropic radiator to calculate the gain of an antenna. But what happened here? A practical antenna will work in a given particular theta direction. So that's why that particular direction is to be used to obtain the gain of that antenna there in the given particular direction. So means y direction, because antenna satellite antenna radiates the signal toward the earth now. So means that directivity toward the earth, or that signal transmitting from that antenna toward the earth there. So that's why that angle is toward the earth now. So that's why it is have a highly direction one. If we have say that if your beam is a narrow beam, okay, if that antenna have the narrow beam, then it is about a highly directional antenna. If that antenna is a highly directional or a narrow beam, then that gain will be large. So means we can say that the gain of that antenna is depending upon that what will be the directivity, or what will be the direction in which your signal is propagating there. So that's why we consider that a radiation in a given particular direction, and then we can find out that a gain of that antenna in the given direction there. So if it is to be isotropic radiator is to be used, then no need to consider that it is in a given particular radiation. So we can consider that total power radiated by that antenna, and then we can calculate that radiation intensity in the given direction, and using that we can calculate the gain of that antenna. Means gain is nothing but what? Whatever the radiation intensity from from a practical antenna, from a practical antenna in the theta direction, okay, in the theta direction, with respect to that total power by 4 pi. So we'll get that gain in the theta direction. Next fact is about a polarization there. So in the case of a polarization, what will be the orientation of a electric field component? Polarization means what? Your antenna radiates the signal in all the directions. Suppose we say that this one is about your dipole. Okay, so around that, here we can consider that a electric field is likewise. This is about your electric field now. And then because this one is a wire, so around that there will be a field component that we can say that is about a magnetic field component. So, So now the direction of this electric field vector, okay, because if you consider that, if you close it here, and if you see that, so these are about your electric field component and magnetic field components are perpendicular to each other. So in a polarization, we need to know about that what will be the orientation of electric field component. Now in general case, if you see that AM communication, okay, amplitude modulation, okay, or you can say that FM modulation. So in that case, that antenna most of the time, that antenna is used is a vertical one. Okay, it is not just like I have a ground and it is perpendicular to the ground. Means we'll say that that antenna is a vertical. No, that antenna will provide that electric field component that will be perpendicular to this particular ground plane. Then and then we can say that that antenna provides the that electric means electrical field component that will be perpendicular to the plane. So then and then that antenna is called as a vertical antenna. So if that antenna generally even if we see that a vertical wire, okay, even if we say that rod is there, so around that electric field is there that is perpendicular to the plane now. That's why it is about a vertical antenna. If you consider this one, so electric field component is parallel to the plane. Okay, electric field components will be parallel to the plane. So that's why it is called as a that we can say a parallel antenna or a horizontal antenna. So orientation of the electric field component will gives us the polarization pattern. So polarization means what? There are the types of polarization. We can say it is about a linear polarization. So in this case, we can say a vertical polarization. Then we can say it is about a horizontal one, or we can say that is about a theta polarization. Vertical field component, electric field component vertical, electric field component horizontal. Here the vertical is nothing but what? A perpendicular one. Or here we can say that is about a parallel one. Okay, I'll write here perpendicular, then a parallel. Okay, vertical means perpendicular one. Horizontal means parallel. So that polarization is called as a vertical polarization or a horizontal polarization. Then another is about a circular polarization. Now that orientation of that electric field we say here it is a perpendicular or a parallel, we can say it is about a vertical or a horizontal polarization. But in the case of a circular polarization, that electric field move in a circular fashion. Okay, supposed to be direction of a propagation is likewise. So then our electric field vector will be propagating in a circular fashion. Likewise, this one is about a circular. If you take an example of a spring, okay, if you take an example of a spring, in that case spring has a circular here. So likewise, we are getting the a circular fact, circularly rotating the electric field component. So that is called as a circular polarization. And similarly, we have the elliptical polarization. So that electric field component, while rotating, it makes a ellipse. Likewise, instead of in a circular what, looks like a circular one. Electric field component makes a circle. But in the case of electric field component, in the case of elliptical polarization, it makes a okay ellipse one. Okay, while rotating, it will make a ellipse. Likewise, so we can say that is about a elliptical polarization. So we can find out on along with that circular polarization, we can say that whether your signal is propagating in the forward direction or in the opposite direction, or you can say that A right hand circular polarization or left hand circular polarization. So they have the types of a circular polarization. Similarly, we have the elliptical polarization. We can say that it will rotate in the elliptical fashion. So that's why the elliptical polarization. The next parameter is about the beam shape, or we can say that, or there may be a multiple beams. They may have the multiple beams there. Okay, beam shape it whether it will be of what will be the area coverage. Okay, coverage area or a coverage region. Okay, it is depending upon that shape of the beam, or we can say that it is totally depending upon that what will be the shape of the what we can say that the body of that particular beam. So we should know that what will be the coverage area of that antenna, or how many multiple beams are propagating through the antenna there. So generally the beam shape is always circular. It will be always circular in a shape. All the beams always in a circular in a shape. But if you consider that antenna, if it is a dish one or a circular one, so you'll get that a circular fashion. And they are feeding with a different antennas. So supposed to be we consider that that antenna is not in a circular in a shape. So then what will be the shape of the particular beam there? So if we consider that a horn antenna is to be there, so then it produces a non-circular shape of the beam there. So different means according to that type of an antenna, so we'll get that a specific shape of that antenna there. Specific shape of the beam. It is totally depending upon that how your signal radiating from the antenna. According to that, we'll get that various beam shape, or we'll get that various beams of the antenna. Then we say that a multiple beams, or we can say that a number of beams there. So if supposed to be we are using a reflector antenna, okay, if we are using a reflector antenna now, so this is about a here they have the multiple dipoles are used in the given reflector. They have the multiple dipoles used. So in that case, each and every dipole they provide a different shapes or a different beams there. Okay, so we use a multiple feeding element. Okay, these are nothing but a various feeding element. Okay, various feeding elements, and that multiple feeding element that provides a multiple beams, because that reflector is a single reflector. We have the single reflector here. Okay, this is about a single reflector, but using that single reflector we are using the multiple dipole antenna. So using that we are getting the multiple beams there. Okay, same antenna with same reflector, but we are using a multiple feeding elements. So that's why we are getting that multiple beams of that antenna there. So that's why if you consider that this particular antenna is present, even if you see that all the antennas are on the same particular axis, but when we come on the earth axis, so in that case it is just like a coverage area for this different antenna will be different. I mean, this is about a more spot of this particular antenna. This one is nothing but a spot. Separate spots are generated on this region or that, but on the earth itself there. So that's why we can say that it is about a beam shape. If it is a narrow, and if we are using multiple feeding elements, there will be multiple shape, or sorry, multiple beam, and they have the narrow shape of that narrow shape of this particular beam is there. So multiple feeding elements, multiple beams will be there. Multiple, that shape is depending upon that what type of an antenna is to be used. And then another parameter we need to be considered, that is about a side lobe performance. In the case of a side lobe performance, generally a antenna has a main radiation pattern, and then along with that they have some sort of particular side lobes occur. This one is about your main lobe now, and then we have the side lobes, and then a back lobe. So radiation pattern of an antenna, in this case, this one is about your main beam, or we can say that is about a bore site of an antenna. In that case, maximum radiation there, and they have the many side lobes. But main radiation pattern have the large power. Okay, they have the large power, and these particular side lobes, if you consider that, they have the lower power or lower energy radiated from this particular side lobes there, and that lower energy in particular direction only or particular place only. But along with that, through that particular main lobe and this particular side lobe, there is a null. This one is about a null here, null occur, and that null occurs means there is that region coverage is small. Okay, now this a side lobe performance, we say that this one is about a side lobe, and that energy radiated from the side lobes is about a lobe, and main lobe, that radiation will be larger, intensity will be higher here, and here the intensity of the radiation intensity is small here. Okay, radiation intensity is small, but radiation intensity in this case it is about a large one, and due to that your signal transmitting from this antenna, if we consider that a radiation in the given direction or a desired direction, so means we are expecting only this this signal is nothing but a desired direction signal. And these are about the side lobes, just like it is about a loss, or it is just like a splitting of this particular main beam into the various side lobes there. That is about a side lobe performance. So this side lobes will give, we can say that they have the lower energy, and they are just like a reduction in this power of this particular main lobe there. So if that side lobes are removed, then gain will be increased, or this main lobe will be increased there. Then a power handling capacity. So if you consider the given antenna, and that will work for the maximum power. So when we consider that antenna work for the maximum power, in that case, they should have to work better, and they should have the low loss there. Okay, or you can say that's about a VSWR or a return loss, and they has to be lower there. To me, performance or a power handling capacity of that antenna It depends upon that what will be the VSWR ratio or what will be the return loss there. If that return loss will be increases, we can say that. So in that particular case, that power reflected from this given antenna, or we can say that we have the a power amplifier here, and after that we say we are using the antenna. Sorry, here is the antenna. Now it generate a high power and it will connect to the antenna. When it will connect to the antenna, it's supposed to be if the handling capability is not large, so then there may be a return loss, or you can say that we can say that is about a AVSWR at this particular point. So that antenna will reflect that if power from this because that handling capability is not large, so then it will be reflect that particular power. So that's why the return loss will be more there. And due to that, okay, due to that, a power amplifier may damage because of that return loss. So we should know that what will be the power handling capacity of the given particular antenna there. Then we should know that a weight of that antenna because a total weight of that antenna, sorry, total satellite weight, they consist of that weight of that antenna also. Means if we increase the size of that antenna, so total overall weight of the satellite will be increased. So we consider that a weight is to be minimized so that a launching cost of the satellite will be minimized there. Then a material is to be used in a satellite that is to be a lightweight material. If we use a lightweight material or with a good conductor, okay, if we have the good conductor with a lightweight, then a loss will be minimized. Okay, so we can reduce the losses in the given antenna there. And because of that reduction in the losses, we will get that a high gain or a maximum radiation in the given direction. So to achieve this particular lightweight and a good conductor, so mostly if you see that nowadays a aluminum is used. But if you consider that a aluminum and a copper, suppose, so in that case, that copper conductivity of a copper is a good as compared to the aluminum. But if you consider the cost wise, then aluminum is good. And then that is about a good conductor as well as a lightweight and a cost is a less. So that's why that aluminum is to be used in a satellite because it fulfills the criteria for the lightweight at a good conductor there. Then that antenna having the dimensions that will be suitable for the given antenna to be used in a satellite or that antenna is to be used in a space. If we consider that a antenna is to be used having the large dimension, then weight and other factors will come in a picture, and then it will not it will be difficult to launch that particular antenna. So when we consider that a satellite to be launched or that particular spacecraft we have, and through that spacecraft satellite is to be launched, in that case that dimensions of that satellite, that antenna, will not create a problem for the launching of the satellite there. So that and that's why that antenna is to be a fold. It will be a folded inside the in a particular cylindrical structure, and once it is launched, then it will be open up, and then So that's why we need to consider that antenna dimensions is most important in the satellite, because we are launching the satellite in a given particular orbit. So that antenna to be a folded one. And then last point is about a steerability. So steerability, if that weight of that antenna is large, so then achieving that antenna, or we can say that radiating the signal in the given direction will not be achieved. So that that antenna can be moved in any direction, or toward the pointing toward the earth station, so that we'll get that maximum power, and on, or that earth station will get the maximum power there. That is about the